It's really nice to have the recently arrived Roy Shalev to tell us about recent results in this vector of uncountable objects. So this is part one, and part two will be beginning of April because reasons.
Thank you very much, Sensor. It's really great to be here. Finally, it took a lot of time. So yeah, I think I was a bit shy at the last two seminar talks, but I'm Roy now. Now I must be not shy. Yeah, I'm gonna tell you about some project for my PhD. Um, okay, so the plan for today is to start with some introduction to everything you're going to see today. Hopefully not too many introduction. And then after I plan to get to some questions, which I think are kind of arising from everything I will discuss at the start. And then I will show you the list dichotomy and some applications, and we will talk about consistency. It's a bit short talk, so I don't know if how far we get, but let's try to see some things. Okay, so it's important to say that this is a joint work with Todorcevich and Kuzelevich, Borisha. Okay, so the start of this talk is Martin axiom. So as you are all familiar, right, Martin axiom is the first forcing axiom that we have, and it is a very nice thing, right? You can use it when you are you don't have to do iteration of some argument, and you can just use this very nice forcing axiom to get some nice results on the structure of objects or topology or whatever you like. It was pretty powerful and useful along the years. But let's try to remember where it came from. It came from the proof of Shalev and Tenenbaum for the consistency of the Susnin hypothesis. Okay, so just to okay, let's start with this. Okay, maybe let's be a bit smart for it implies the Susnin hypothesis, which says for this talk, let's look at the equivalent form of trees. So it says that for every aleph1 tree, there exists an uncountable antichain. So okay, so this is the start of the how Martin axiom was done, and also they got an even stronger thing, which is that every aleph1 tree is special. Okay, so I will call this statement the special Arnstein tree property at aleph1, and it says it implies the Susnin hypothesis, of course, and so okay, so what is special? Special is just saying that let's say that for every aleph1 tree, Arnstein, which says that no branch or no uncountable branch is a union of countably many antichains. So usually the basic, where does it come from, this special notion? So the special notion comes from, right, the first Arnstein tree you usually see is a special one. It's constructed from these rationals. There is an embedding of the tree to the rationals, and this gives you this nice property. And so the first thing I would like you to think about is usually, so when you want to understand the structure of some object or just to understand in general, you look at the first example you have, and you ask, okay, what are the properties of that? So in this case, we know that it is special. And the first thing you can ask is, okay, can it be that always it is special? It must have this property. This is kind of a big direction for this talk. All right.
One clarification.
Yeah.
When you say all in one tree, you mean countable limits.
Yes, countable levels. Yeah, that's my notion. Sorry, yeah. All right. So, okay, but I want to also add this nice thing that it took me a while to understand this, but actually this special arbitrary property is actually a statement which is a dichotomy. Okay, it's saying that every Aleph1 tree either has a branch, okay, or if it doesn't have a branch, then it is Aronshine, then it is a union of countably many antichains, okay, and it might look very obvious now, but I think that it took me a while to understand. But you can view this thing as a dichotomy about the class of Aleph1 trees. All right, so what I want to claim now is that actually this dichotomy or property of Aleph1 trees is actually something that we, if we look at applications of Martin axiom, we see again and again and again. So the next example I want to present here is about something called omega 1 towers. So okay, let's go there. Why not? So our second object for today is going to be that. So an omega 1 tower is the following object. It's a sequence T of length omega 1, as it says in the omega 1, which is of elements in P omega, which is chain modulo bounded or modulo finite, whatever. Like, let's talk about modulo bounded in our case because we want to generalize it later. Chain such that actually it's a strong chain, meaning that if T alpha is a subset modulo bounded of T beta, then this happens if and only if alpha is less than beta. So this condition actually says we are increasing by infinitely amount each time. Okay, so this is a very nice object, obviously. And now let's look at what is a Suslin for this object. So a Suslin would be a large antichain. Okay, so T is called Suslin if for every okay, let's say if there are no uncountable antichains in the full order of a subset. And what it would be special? So again, Suslin and special are the overhand of our spectrum for an object. So a special would be if there exists a map from omega 1 to omega, so you can partition it to omega many, to countably many elements, such that if you have that C alpha is equal to C beta, then let's say alpha is less than beta, then T alpha is not a subset of T beta. It is an antichain, all right? Okay, so what do you expect Martin axiom to do to these objects? Specialize all of them, right? So okay, so it is specializing, but let's give just for now, there is even a stronger property, which is called Hausdorff. I will just write it. So T is Hausdorff. I think this is a bit diverging from the regular definition. The regular definition is that there exists a Hausdorff thing. I'm calling the Hausdorff something a bit stronger, which is there exists a coloring for omega 1 to omega, such that for every I less than omega, and for every j, let's say for every I and j, if we look at all the x's which get color the same as I, below alpha, one second, I think I just want to say that the coloring of alpha is I. Okay, so for every alpha less than omega 1, such that. All right, so Hausdorff is a bit stronger. It's saying not only that it is special, it's saying that you have below you a witness of the okay. Okay, you know what? Let's not try to motivate it. I don't want.
You mean you can break it into countable many pieces, each of which has the Hausdorff property?
Yeah, the Hausdorff property. Yeah. So okay. Anyway, if you're familiar with the Hausdorff for gaps or for towers, it's good that you. But let's skip it for now. I don't want to waste time motivating it too much. But what I want to say now is that there are more examples such that for different objects like gaps, there is a specialization or Hausdorffness of gaps. There is the something called Arnstein semilattice, which also has this phenomena of specialness. And there is something called strongly unbounded coloring, which is related to B, to the B number. And also there is something about directed sets. Okay, so obviously, what I want to claim here until now is that a bunch of objects which are quite natural and we like them as a set theorist has this phenomena of specialization under Martin axiom. So from this introduction, I hope I can motivate a few questions that arise to me for this. So, okay, so one question is how much of MA is needed? So this is related to the questions about fragments of Martin axiom and how they are interacting and what imply the other thing. It will occur again for the third question. Why is it important? And it turns out that, as I will tell you in the next things, is that Martin axiom for YCC posets is actually quite nice, and you can also see it in the literature that many of these things that I just mentioned coming from MAYCC. Okay, second thing is, okay, we see a lot of these flowers, a lot of these things which behave special in some sense. Can you unify them? Like, can this all come from the same object? So can you unify these results? And the third one, which I like the most, is what about higher analogs? For successor of regular cardinal. So
GCH below the regular, or just?
You can add, which I'm not, this is, yeah, like it was general, like just, yeah. Okay, so about the third question, I know about only two results which kind of generalized from Martin axiom or PFA to higher analogs for this kind of objects, and it is the Sustin hypothesis or the special Arnstein tree property for Aleph2 or whatever successor of regular cardinal, and there is also some stronger result about the structure of Aleph2 trees by Kruger, that every two Aleph2 sigma closed Arnstein trees are club isomorphic. Okay, so this is a result which was generalized from Aleph1 by Avraham Shelach to Aleph2 which is a Kruger result. All right. So okay, so this leads us to this talk, which is about the list dichotomy. So I would like to next introduce you to this dichotomy that we have, and show you some of the examples of application of it, and later on we will talk about the consistency of it. Okay, so all right, so let's start with some definition. So we are trying to unify all these objects that we see before: trees, gaps, towers, directed sets, semi-lattices, strongly bounded coloring, or all these things. So the suggested object is the following. It is something we call a kappa list or a lambda plus list. So a sequence L, which is, let's call it, so let's assume in the background that we have lambda is regular, cardinal. So a sequence L is a lambda plus list if it satisfies the following two things, which is that for every delta we have that L delta is a subset of delta. So we do have some smallness, it doesn't grow too far. And now that we have one set for every level, we can ask for every index we have one set, we can ask, okay, what is the level of everything which is of the same level? So let's call the level alpha of the list to be all delta below lambda plus, all indexes where the order type of L delta intersection with, of L delta is just alpha. Okay, so the alpha level is all delta which has the same order type delta. All delta which has the order type alpha. And now the second requirement here would be that the level is small. So the level, so let's do it 2. For every alpha less than lambda plus, we require that it's big. For every alpha less than lambda plus, the level alpha of the list would be of size less than or equal to lambda. So why does that make sense, to limit ourselves to small levels? So if you look at trees, right, the levels are small. So like if you consider the notion of what I'm talking about, of lambda plus Aaron-Chain trees or whatever, and it turns out that this is good enough. It's nice for our behavior. And another property would be 3, that we require the list to be transitive. We do want some structure on it. So L is transitive if for every gamma less than delta less than lambda plus, gamma inside of the list element L delta would require that L gamma would be a subset of L delta. Okay, we do have some nice transitivity assumption. Okay, denote TL lambda plus all lambda plus transitive lists. Okay, so an element in TL lambda plus would be just a transitive list of lambda plus. I will say that I'm a bit simplifying. I can also have some support for the list, which is different, and I can also have a dichotomy which is simultaneous of lambda many objects. But let's keep it simple for now. No, what should what?
You're on the rear most. So go to the next board.
Just go to the next board. Okay, okay.
This time.
Maybe
bring
pull,
that-
but maybe
bring
pull the
that
middle one
down.
down.
That will. Okay, I don't know. Okay, I did one. Okay, yeah.
These lists, do you care about the successor ordinals in Lambda Plus, or are are they important, or?
What do you mean?
Well, because you could have a list just for the limit ordinals less than that plus.
Yeah, so
Is it pretty much the same?
I think it like if you allow the support to change, then it is kind of the same. I think it will be the same thing, but it's not just redundant. Like you miss some things. Okay, just make it more sparse. It doesn't change. All right. So what is the definition of the dichotomy? So the list dichotomy at lambda plus is the assertion that for every list, transitive list, lambda plus, either two things happen. So the first one is saying that you have some A large of size lambda plus in lambda plus, such that whenever you look at initial segment of it, let's do alpha, you can find some delta alpha below lambda plus, such that the initial segment A intersection alpha will be a subset of L delta alpha. Okay, so for every the first alternative saying that there exists a large set such that any initial segment of it is covered by one element in the list. Okay, the second alternative, so this is like the branch. There exists a branch alternative. Okay, we'll see some examples later on. The second thing would be, oh, sorry, yeah, I forgot something. Okay, I do need some notation here, but it's good. Given L, some list, we define a measuring map. So the measuring map will measure X subset of lambda plus, and intuitively we would like to know how many sets from the list, what is the minimal size of sets in the list you need to cover your set X. Okay, so the measure of X by the list L would be the minimal theta, such that theta is equal to kappa to lambda, so lambda plus, it is maximal, or you can find some f of size theta in lambda plus. You can have theta many indexes from the list, such that the X will be covered by the union of L beta, where beta is in F. All right, so it is the minimal size theta of subset F of size, but there exists some subset F of size theta which covers your set X. Okay, so it is like measuring. If you have, so not like, let's just see some examples. So if you look at one set from the list itself, the covering going to be one, right? You need one set to cover it. Obviously, if you're giving me a very big set, like a cofinally lambda plus, you cannot cover it with small amount, right? Because the elements in the list are bounded. Okay, so using this measuring thing, we can define the clause 2, which says that there exists some partition, AI, I less than lambda, partition of lambda plus, such that whenever you look at some element in the partition, some I, for every small set in AI, in one of the set in the partition of size small, of size lambda, the measuring would have to be big. Okay, so don't worry, I'm giving you a weaker assumption, which is much easier. So the free clause, so it is a dichotomy. There is only one or two. Let's do 2 prime. Let's do 2 prime. Let's make it easier for you. So 2 prime is a weaker thing. Okay, it's going to be implied by 2. Okay, let's be even more clear. 2 implies 2 prime. 2 prime is the following. It's saying that you have some specialization map. You have a map from lambda plus to lambda. Okay, such that whenever you give me some gamma and delta in lambda plus, and they get the same color, C gamma is equal to C delta, then gamma is not going to be inside of L delta. So this is the anti-chain property. You have a partition to lambda many sets of the full size, such that whenever you give me the same color, gamma will not be inside of L delta. You can now define a relation of gamma and delta to be related if gamma is inside of L delta. So now it is an anti-chain. So it is a partition to lambda many anti-chains. So in some sense, the first alternative is saying, you know what, there is some branch, okay? And the second is saying, okay, it is special. There is a very nice way to see that there are no branches. All right. Okay, so as I said, I'm not going to bother today to discuss the simultaneous definition, but there is some simultaneous definition which give us, for example, that every omega 1 tower is Hausdorff. Okay, you need the simultaneous to get the stronger things.
You mean,
Hmm?
I didn't understand what you just said. What do you mean by simultaneous?
I'm saying there is LD lambda plus lambda, which talks about lambda many lists together, and saying none of them has a branch,
Yeah,
and the
okay.
second saying you specialize all of them simultaneously.
Okay.
Is this notion addressing question 2 you have there about trying to
Yeah.
unify the result? Okay.
Yeah. So
That doesn't follow from this? though?
what?
The uniform version, I mean, the simultaneous version?
I don't know.
Because
No, because it is.
if you give me lambda many lists, you can sort of amalgamate them. Using, anyway, I don't know.
But it is. I don't know. I wasn't able to prove this. I didn't try hard enough. I didn't separate them. But
Okay, so you don't know whether it's the
like
same.
no. But I do know that. Like I do know that some fragments of Martin axiom I know how to prove very easily that the list dichotomy follows from them, and for stronger ones I'm it's like none, like I have no idea. So okay, so how's the time? Great. All right, so now it's the time for a bunch of theorems. Just to tell you, like I gave you some definition. Let's see what we are able to do with it. So the first theorem is about consistency. So MA aleph 1 or even YCC imply that you get the least dichotomy for omega 1 and also for the simultaneous one, whatever. Okay, and
So,
yes.
If I remember correctly, this MAYCC, you don't add random rates.
Yes.
You can force this without adding random rates.
Yes. So yeah, so I get that the least dichotomy is consistent with the covering of Meager being aleph 1. And also that if you're curious, also we get that it is consistent with the existence of an entangled set of fields. So there is some limitations about this. The dichotomy doesn't imply everything. It's not a MA. Yeah. And it has some, yeah, it doesn't apply to every combinatorial assumption that we know. It is restricted. Okay, but this might be the reason that we are able to do the next part of the theorem, that suppose there exists kappa weakly compact cardinal then there exists P in poset such that In VP, we have diamond omega 1. I know it implies it, but we also have CH, just to be clear. And also we have the least dichotomy at the level of omega 2 and the simultaneous omega 1 many times. Okay, so yeah, so it is using the label Shalach ideas, but we do have, I'll get there at the end, we do have some new thing that makes it work here. But
You said it, but I wasn't.
Yeah, sure.
What's the
what is the simultaneous?
Simultaneous.
Yeah, so the simultaneous is the first one. It's like about lambda many list. The first one is saying that that there exists a lambda plus size such that for some element of some list of them of the lambda many is satisfying that. Okay, this will be the first alternative. And the second is specializing all of them together. So like the measuring is with respect to a specific list in the list of lists.
So one happens for one of them.
Yeah.
Or you can get two for all of them.
Yes, yeah. Like if you have branch for one of the trees, then I cannot do specializing of all of them together. But if all of them are Aronshine, then I can specialize them all together. All right. Okay, so this is in terms of consistency. The next theorem is about applications. So again, everything I'm talking today is about regular cardinal lambda, just to be clear. So the next thing is about the application of this list dichotomy. So it implies the following things. So first, it implies that every Aronshine tree of size lambda plus is special. Okay, so we extend the label Shalach result. Second thing is that we actually get a bit. Yeah.
Tree of size lambda plus. Do you mean lambda?
Lambda plus Aronshine trees. Yeah. Every lambda plus Aronshine tree is special. All right. The second thing is that we get every lambda plus Aronshine semi-lattice, which is some generalization of Aronshine trees, is special. A bit about that. Okay, so it was I don't remember the first person which did it, but this notion, there is a paper by Dilip and Yorioka where they investigate the relation of the Aronshine semi-lattices which are special and trees, and they have a bunch of very interesting results. I encourage you to have a look at this paper. Okay, next thing is about gaps. So
Wait, this doesn't solve does this solve the question of whether CH implies?
No,
Okay.
no.
Because I think that's okay.
That's open. That's open.
fine, check.
Yeah, it's a different question because here it's about specializing everything. It's
Okay.
yeah.
What was the CH question?
The CH implies there is a solution. This is still open. It's not settled.
It is related to the PID and things. Yeah.
What we did in our papers, we tried to solve this, but got much further. Didn't solve it.
Okay, so assuming lambda to the less than lambda is lambda, so here we do need some cardinal arithmetic. There are no Todorchovich gaps in P lambda modulo bounded. And the reason that here we are talking about Todorchovich gaps and not regular special gaps is that Todorchovich gaps is a second dimensional object which is transitive. And so we can handle it. But later on in the third theorem, I'm gonna say that we also solve it for Hausdorff gaps, but that's something for the later theorem. but not using this list dichotomy. It requires some different idea. Okay.
So one question.
Yeah.
So this L v lambda plus lambda, I mean, do you have models where it's true other than omega 2?
Yeah, it's for every regular the same way that Lever Shalach
Okay.
works.
Okay.
Yeah. I just didn't bother writing it down, but it is the same. All right. So the fourth one is about towers. So every lambda plus tower in P lambda, again, modulo bounded, is Hausdorff. Saying also this implies that all of them are special. Yeah, all right. Okay, 5 is saying that in the case that lambda is Aleph 0, then the list dichotomy implies that the bounding number is greater than Aleph 1. And for lambda equal Aleph 1, for example, assuming diamond at Aleph 1, we get that Aleph 1 is less than the dominating number. Dominating number of Aleph 1. So we do have some results about cardinal characteristics from this. The reason is that here we go from dominating from bounding, is that at Aleph 1, the bounding number implies that there is some strong unbounded coloring, and for the Aleph 1 case, you need to do for Aleph 2, you need to go for the dominating for that to achieve this. All right. Yeah, I think if there is some result about directed sets, maybe I'll say it. The third result says that under LD omega 2 omega 1, every Aleph 2 every directed set of cofinality lambda Aleph 2 sigma closed which it is long, which every lambda plus Aleph 2 that contains an unbounded Aleph 1 subset is Aleph 2 CC indestructible, destructible by sigma closed forcing by some. Yeah, it is long, but this is what initiated all the project, trying to get okay, so instead of looking at that, there is like a result of Stevo from the 5-element basis paper of the final types. But okay, he has the paper where he proves that from PFA, there are only 5 cofinal types. And then he looks at what happens under Martin axiom. So here we get some kind of generalization of that for the next element, but because we don't have Martin axiom for Aleph 2 in the background, we only get that it is destructible by someone. Yeah, so this is kind of, yeah.
So regarding fun,
Yeah.
Do you know if you get the Bushnick Miller
No.
step it up to?
I think this is not, again, it's not transitive. So it requires more stronger things, but
So you don't know if you get omega 1 out of something, omega plus 2.
no, but because of the less of the, yeah, let's, no, how does it work? Okay, I try. Because of the next theorem, maybe there is hope. So the last theorem for today is about gaps at Aleph 2. So theorem. So this is by Todorcevich and me, that consistently, again, like this from a weakly compact and there is a P, whatever. So consistently, every omega 2 gap in P omega 1 modulo bounded is Hausdorff. And we get even more, and all gap types are of the form omega 3, omega 1, omega 1, omega 3, and omega 2, omega 2. So this is generalizing what we know about Martin axiom for the next cardinal about gaps. All right. So the last thing before we talk about the consistency, let's see how the time is. Okay. Okay, so the last thing I want to say is that no, okay, I didn't do applications. Okay, yeah, I do have time. All right. So I want to say that all these things that we discussed, all these objects and kind of theorems from Aleph 1, some of them are following from some dichotomy we have at Aleph 1, like the P ideals, which imply that there are no Suslin trees or Suslin towers or whatever. And there is the small ideal dichotomy, which implies some of this result, or the open graph axiom. So it is kind of joining the family of dichotomies that we already have. All right. Okay, let's see some examples for the use of it. So applications. So let's start with trees. So okay, so example. So let's assume that we have some tree T where the ordinal, it is ordinal based, okay? Every tree can be is isomorphic to an ordinal based one, where by ordinal based one I'm saying a lambda plus, okay, lambda plus B. So the levels are of size less than equal to lambda. So what do I mean by ordinal based? I mean that the order of the tree is behaving nicely with the order of the ordinals, and the set of the tree is lambda plus, is the, yeah. So it means that gamma is less than delta by the tree implies that it is by the order. Okay, so for now we want to define a list. So for delta in less than lambda plus, this is an element, a node in the tree, right? So we would like to assign it some subset of delta. And by the fact that this is ordinal based, we can look in the downward cone. Okay, so L delta is going to be the downward cone of the tree, which is all gamma below delta, such that gamma is below in the tree delta. Okay, so this generates from the tree a very nice list, and it is very easy to prove that L, which is defined to be L delta, where delta is less than lambda plus, is a transitive list, transitive lambda plus list. All right, so now we have the dichotomy implying that every Ahrenstein tree is special. So let's keep that. Let's do this. So a lemma. suppose you have LD omega 1 holds. If L satisfies the first alternative, then what does it say? It says that we have some A
Omega one or lambda plus?
omega 1 left. We can do lambda plus. Let's do it. It doesn't matter. It's the same. So let's look at lambda plus. So we have some very big sets such that for every initial segment of it, alpha below lambda plus, we have some delta alpha in lambda plus covering A intersection alpha. So pick gamma less than beta in A. We are going to claim that this is a chain. All right. So this is covered by some delta alpha, right? So gamma and beta are inside of L delta alpha for some alpha. But this says that gamma and beta are below in the tree order delta alpha. So this is a chain because everything below a node in the tree is a chain. All right. So A is lambda plus chain. So T is not Aron chain. So regarding the second alternative, this is implying that there exists some coloring C from lambda plus to lambda, so such that if alpha less than beta less than lambda plus get the same color, then alpha is not inside of L beta. But this implies that alpha is not below beta in the tree order. And because this is ordinal based, we don't have the over case because beta is above alpha in the ordinal based. So we actually got a partition to lambda many antichains. So it is special. So in the second alternative, T is special. So whenever you give me a lambda plus Aron chain tree, it is isomorphic to some ordinal based tree. And because it doesn't have a branch, it doesn't have a lambda plus chain, it doesn't satisfy the first alternative. It must satisfy the second alternative, so it is special. All right. Let's see the towers example. So the next lemma, I want to prove that LD omega 1 imply every omega 1 tower is special. All right, so we are given an object from here. Yeah, I think, all right. So we are given an object in a list, a sequence of subset in P omega, sorry, such that it is a chain modulo bounded, and at every coordinate you increase by infinitely amount. All right, this is the object, and we want to prove that it is special, meaning that it is a countable union of antichains, or there exists this map C from omega 1 to omega, such that if you assign the same color to alpha and beta, then T alpha is not a subset of T beta. All right. So first of all, we need to define some list. Okay. Okay, let's fix T alpha and omega 1 tower. Yeah, we would like to show that. Okay, so let's define a list. So okay, so this is actually regarding towers. It's in order to define the list, it is, I think, the only construction where we don't look at the downward cone, because you need to prove somehow that the levels are small. So in order to do that, I need to do some stretching of the list. So let's see. So define L by, okay, let's do, okay, so define a sequence S, which is going to be S alpha for alpha less than lambda plus by letting S of lambda alpha times alpha. Okay, let's do omega 1, sorry. Omega times alpha plus some I to be T of alpha minus the initial I. So for some alpha less than omega 1 and I less than omega.
You're mixing lambda plus and omega 1.
Well, so yeah, sorry, this is omega 1, yeah. We'll only do omega 1. Let's do the simple case.
Yeah, but that's now a subset of omega.
Yes, we are looking at a subset of P omega, right?
Yeah, so but okay, so but your S alpha then is just always a subset of omega. It's not a
Yes,
subset of
yeah, it's not a subset of alpha.
alpha.
It is a
No.
subset.
Okay.
It is also,
It's a
okay.
subset.
If alpha is big enough.
I mean, it's bounded.
No, if alpha is big enough, okay, yeah. All right, so, yeah, so I'm defining now a new sequence by stretching out. So look, the first, for T0, so S0 would be like T0. But then for S1, we look at, it would be S0 minus the first, without 0. And then S2 would be without 0 and 1, like that, okay? We just remove initial segments from that. All right, so now regarding this object, we can define now the list. So, yeah, it's not the list yet. No, list are with L. Let's keep it a good notation. So, okay, so for alpha less than omega 1, let L alpha to be all beta below alpha, where S beta is a subset of S alpha. Okay, so, all right. So now it looks transitive, right? If you have a transitive order here, you're going to be transitive. Okay, so let's keep it as homework that the sequence L defined by L alpha, alpha less than omega 1, is a transitive list for omega 1. Right? It's clear to see that it is transitive. It is clear that it is every alpha, L alpha is a subset of alpha, obviously. And it is not very hard to see and check that the levels are of small size. Why is that? Because let's have a picture. We have here omega 1, and we look at some S alpha. No, let's look at alpha. So alpha is going to be some omega times lambda plus some I, right? So now I'm claiming that it is the order type of L alpha is at least lambda, because it is a sequence increasing modulo bounded. So if you remove some place from before, at some point you're going to be below. Okay, so because we do the stretching, it's going to be of order type at least lambda. All right, so I hope I convinced you that intuitively, at least, the levels are small. So, okay, now we can apply the two alternative. So we split to two alternatives. So the first alternative, we assume that we have some A. Let's do subset of omega 1, uncountable, such that whenever you give me some initial segment of it, you have some witness that it is covered by one set from the list. So for every alpha, A alpha intersection alpha is going to be a subset of some L delta alpha. Okay. Can I erase this one? Yeah, let's do opposite. Okay. Okay, so we are in the first alternative. So let's prove that the first alternative always fails. Okay, so we are aiming for some contradiction. So let's W to be the following nice sets. It's going to be the union over all beta in A, S beta. It is, and every S beta is a subset of lambda, right? So we are doing some kind of exaction of, like, yeah, I'm not pronouncing it right, but exaction of indexes. Okay, so this is a subset of size lambda, and the index set is of size lambda plus. So we can pick a witness for every element in W, what the minimal index of it, and this is going to lead us to a contradiction. So for every eta inside of W, pick minimal.
Sorry, I'm getting it also by the lambdas and whatnot.
Ah, sorry, yeah, you're right. Omega.
S beta is all substance of omega.
Yes.
That's just trivial.
Yes, that's a trivial. Yeah. Okay.
I thought
You're right. Fix me every time because I might. Yeah. Okay. All right. So for every eta in W, we pick a minimal beta eta in A, such that.
You should repeat that.
Okay. Yes, that's a very simple thing to do.
Thank you.
Yes. Beta n. Yeah, beta n is in A, such that n is inside of L beta n. All right? No, you're all right. You're all right. Thank you. All right. So we have this witness. Now we can pick some alpha in A, which is going to be above all the witnesses. So it's going to be above the soup of beta n, n less than n in W. Okay, and now let's go even further. Okay, now we have this. Let's try to do also a picture. We have omega 1, and we have this alpha in A. Now I'm gonna look at delta alpha. Okay, and I want to go even above. I want to go at some delta alpha plus omega, and I want to go to some gamma even. Okay, let's do even longer omega 1. We have this gamma inside of A. Okay, so pick.
Delta alpha is that supremum?
No. Delta alpha is the witness for this boundless. All right, so pick gamma inside of A. Above, because A is uncountable, we can pick someone above delta alpha plus omega. All right. Okay. Now we have to do a bit of indexes. So find.
So is the plus omega added to the alpha or delta?
No, to the delta alpha. Well, I did. Yeah, no, to the delta.
What? Well, it's not clear.
It's very big. Yes.
I thought it was delta alpha.
No. Just, yeah, I want to push it above. All right. So, okay. So find beta and let's confuse me. So let's do nu, because why not? All right. So now I pick beta and nu and some I and j less than omega. This is less than omega 1. No, let's be equal. Beta, nu, limit points of omega 1, such that gamma is omega times beta plus I. Okay, right, and I can represent it that way. And I want to represent also delta alpha as omega times delta, no delta, sorry, times nu plus j. Okay, so I pick limit ordinals beta and nu, which has this, yeah, okay. All right, now because gamma is omega time more than omega plus delta alpha, we get that this beta is greater than nu. Okay, so beta is greater than nu. So because beta is greater than nu, we get that. Okay, this is important. This will be the end contradiction. All right. Okay, so all right, let's see. Let's notice that.
I don't mean to nitpick, but.
Yeah.
But when you say beta and u are limits, you
Yeah.
really mean omega times beta and omega times mu. Because you don't know that.
No, yeah, you're right.
So
You're
it's
right.
important.
You're right. You're right.
Just wanna make sure.
Yeah, you're right. You're right. This is a limit. This
Yeah,
is a
it's-
yeah. You're right. Yeah. Yeah. Thank you. Uh,
So the interval between delta alpha and delta alpha plus omega is disjoint from A. Does that?
yeah. I don't care. I don't
It
care.
still implies that beta is bigger than mu.
Yeah, beta. Yeah, because gamma is in A. No, like no, gamma is bigger than lambda plus alpha plus omega. So it, like, yeah, you're right. You're right. You're right. Yeah. Okay, you're
Well, you
right.
can choose gamma as big as you want.
Yeah, but I think you do have to choose it so that if there's stuff below A. I
Right,
mean,
right,
if A is disjoint from that interval, got nothing.
Yeah, yeah, you're right. You're right. I want to go even higher. Okay, above such that. Okay, such that this happens. All right. Okay. Good and okay. Sorry. Thank you. All right. Let's see. All right. Now we want to claim that. Where do I want to work? Let's try to do it here. So claim. So I'm claiming that W is a subset of S delta alpha. All right. Right, this, yeah, so pick some N in W. We know that beta N is inside of A intersection alpha. And we know that beta N is inside of L delta alpha. So if beta N is inside of L delta alpha, then this implies that S beta N is a subset of S delta alpha, right? By the definition of the list. Okay, and so eta is inside of S delta alpha, and we are done. Okay, all right. Okay, so let's try to finish this. What do we see now? We get that. Okay, so S gamma is a subset of W. This always happens, right? Because gamma is inside of A. Okay, so S gamma is a subset of W. All right? Okay, so, but what is S gamma? S gamma is actually T beta minus some I by the definition of S gamma. Okay, but W is also a subset of S delta alpha, which is equal to T delta minus J. But beta is greater than, no, okay, here it's no, sorry, here it's no. No. Yeah, so this is by the definition of S. And now we get a contradiction because T beta is now a subset modulo finite of T nu, but beta is greater than nu, which is a contradiction to the way we define the tower. All right? Is it, Paul, was it too?
I just realized I got lost at some point, but that's okay, because I'm looking back and you said N was the element of the L beta N, that was obviously S beta N, but.
S beta N, where?
Because it's the union of these S betas, but,
Yeah.
so I got lost a little bit in this claim here, but that's okay, I think I have the
Yeah.
general ideas.
Okay. Okay. No, you're right. You're right. This is S. This is S. Yeah. I think that.
And then just, I lost the definition. Okay, so L alpha is a set of betas, S beta. Okay, right. Okay. So once you have S beta inside of S alpha. Okay, right.
Enough satisfaction. Should I go over it again or?
No, that's okay.
Okay.
Now.
Okay. Okay. Yeah. Okay.
When you're writing this, I realized I had gotten lost before, and I was
Okay.
catching up. So.
Okay. Okay. So the first alternative leads us to a contradiction. Okay. Let's try to see how. It doesn't go. Okay. Okay. All right. So here we just need to look at this. Like, okay, let's look at the second alternative and show that it is implying the omega-1 tower is special, actually. So, so we have this C here, which satisfies that. Now I'm defining this D map from omega-1 to omega by D of alpha is equal to I if and only if the C of omega times alpha is I. So I'm just reducing the stretch that I did before regarding the coloring C. But this says that now pick.
Who's the coloring C?
So the coloring C is for the list.
Right.
And now D is going to be the coloring of the specialness of the towers. Okay. So now pick alpha less than beta less than omega-1, such that D alpha is equal D beta. But what does it say? It says that C omega times alpha is equal to C omega times beta, which is implying that omega times alpha is not inside of L omega times beta. But what is this? This is saying that S omega alpha is not a subset of S omega beta, but this is, by the definition, this is actually equal to T alpha, not a subset of T beta. So it is an anti-chain. Okay, so the end result is that assuming the least dichotomy at omega-1, every omega-1 tower is special. Okay.
So I have a question.
Yeah.
This shift to the S.
Yeah.
The first part of the.
Yeah.
Is it really necessary to subtract this I?
So I only need it to prove that the levels are small.
I see.
Without
Okay,
that,
yeah, you need these sets to vanish very,
Yeah.
very quickly.
Yeah. Yeah.
As you go up. Okay.
This is actually the first trick I found how to do anything beyond trees, and then I used every time this trick, and then eventually it was the only place that I needed it. Like other places I could change it, but here I'm not sure if it is possible. Like maybe the tower is very weird. I don't know. I'm not sure if it's keep growing. Like modulo. Yeah, I'm not sure.
So it's not really like in the contradiction down here. It's not used that you're subtracting.
No,
Like you
no.
don't care at all.
No,
that
no,
you
no, no, no.
subtracted, Like you
No, I
have
think-
literal.
No, I think the first alternative still will be wrong for the
Yeah.
for the previous one, but for
Uh-huh.
the list that like if you look at the list, like the only question whether the list is small with when you look at the regular tower. Maybe yeah, I don't know. Maybe only maybe here you also can remove this. I'm not yeah, but all right. So okay, so we saw two examples. Let's talk with the time we still have about the consistency of them. How do you prove the theorems of the consistency? Okay, and maybe it's a good step to say, if you think about any other transitive object that has some specialization that I'm not aware of, and please let me know. I will be happy to try to, maybe the list dichotomy works for that also. That would be nice. Okay. And another question is, what is for a topology to be special or something? I don't know what's the right like what would be the right thing to think about? I don't know. What's another question? I'm like trying to find some topology application for the list dichotomy. That could be nice. Okay. So how do you prove the consistency? What should I erase? Let's do this. Okay, so yeah, so how do you force one list dichotomy? You have one list, you want to force that either of the alternative happen. Okay, so usually what you do when you force these things, you assume some of the two alternative fails, and you are able to prove that you have some nice CCCness or some property which is useful to preserve cardinals. Okay, so how to force LD lambda plus, or let's talk about omega 1. Let's be simple. Okay, actually, I want to say another thing here is that I'm not aware of a dichotomy which happens under MA. So I think this is at least what I'm aware of a first dichotomy which happens under MA, where you are able to prove CCCness and you're not proving some properness. So this is a bit different than the regular posit you're aware of for dichotomies. So okay, so how to force LD? So yeah, this is a bit more about specialization, but a bit different. So it is something. Okay, so we assume we have some list in the transitive list of omega 1, and first alternative fail. So we define our poset P by P being, so P is going to be contain some approximation of the partition that we want at the end, but a bit more. So we will have some AI. Okay, so P is a finite domain map, which has domain subset of omega. And for every I in the domain, pi is going to be A, pi, B, pi, where the first coordinate is the approximation of the AI, and the second coordinate is assuring that we get the specialization thing that we want, is achieving the anti-chain or whatever. Okay, so what are the requirements here? Only that this is finite. So where AIP and BIP are finite subset of omega 1. Okay, so being a condition is very simple. Now, all the action is going to happen on the extension. Okay, so Q extend P if the domain of Q is greater than the domain of P. And for every I in this small domain, we have that it is increasing coordinate-wise. So AIP is a subset of AQI, and BPI is a subset of BQI. And now this is coming from Todorchovich paper about the five cofinal types, that for every alpha in, okay, maybe it was before, this is the first place I saw it. Every A new point, so it's going to be in AQI minus API, and for every beta in B, BIP of the small set of the small condition. So yeah, every beta here, we have that alpha is not inside the beta set of the list, the L beta. Okay, so we this is like the commitment that we must respect when we are enlarging the condition, and these are the approximations.
This is, so when you said this paper about the 5 element basis, the 5 of the combined types, you mean the result under MA then about every partial order either contains an uncountable atta chain or is a union uncountably many things, each of which has a upper bound.
Yes.
By the way, do you get that under the dichotomy?
No, you need some you need a bit more. I think you need some I think you use them for that. You use a bit of MA before.
That's right.
Yeah, so this is the part that we don't have. So like this is very interesting actually what you're asking, like how much of MA can you have for larger cardinal? This is a very interesting question in my opinion, and yeah, this is like trying to cross the boundary, trying to see what is Suslin type and what is a bit beyond, which requires some over arguments. Yeah. Okay. So how much time do I have? Okay. Okay, so this poset is CCC. It is actually YCC. And you can obviously generalize it from finite to countable and changing every omega 1 to omega 2, and you get a sigma closed forcing. But question about being omega 2 CC is a bit trickier, right? You need some more. Okay, so for lambda equal to aleph 1, we do Lever Shalev iteration. So we first collapse kappa weakly compact cardinal to omega 2 with sigma closed forcing. And then we do iteration of this thing for upper cardinal. But as I said, the trickier part is showing that each step along the way is going to be kappa CC. Okay, so hard part to assure we have kappa CC. Okay, so I didn't say, so the iteration is of length kappa plus. Kappa CC at C below kappa plus, where we look at P. Like peak C is the C step of the iteration. Okay, so how do you do able to do it? Okay, it works for specific kind of posets. Previously, it was known for this specialized in Arnhem trees. Here we do it for this poset, and you do need some along the way some inductive hypothesis. So Shalev has two inductive hypotheses. We kind of squeeze it to only one. So what is the inductive hypothesis? So okay, I want to say before that this is like a 20 pages proof of the consistency. So it's very hard to compress it to like 3 boards or something. I'm trying to give you the where is the interesting parts where the action happen. So the inductive hypothesis is that for every eta less than some xi, so this is the inductive hypothesis for xi. So for every eta below xi, p eta satisfies something we call U plus cross condition, where U is the pi11 filter from the weakly compact cardinal kappa. So what is a U plus cross condition? It's saying the following. So for every large set W in U plus, so every positive set with respect to the filter, and for every sequence of F alpha, G alpha, let's say, alpha less in W, satisfying that for every alpha in W, F alpha projection to the alpha and G alpha projected to some alpha. So it satisfies this. So whenever you give me this sequence of I didn't say F alpha, G alpha are from the P eta case. So we look at, okay, so what is the U plus cross condition? It says that whenever you give me a large set of indexes and conditions of tuples from P eta indexed by this W, which has a similar projection along the way, you can find some U positive subset of W such that they are cross compatible. Such that for every alpha less than beta in U, we get that F alpha is compatible by P eta with G beta. So this is the cross way.
That's basically what labor and Shalev use.
Yeah, but they don't name it a cross condition, but they have on another thing which this implies. I think they have like, yeah. All right, so how much time do you have?
So there are a bunch of typical things that go into making an iteration like this work. You have this like maybe you have well met or something, and maybe you have these every time you take some chain of pairs,
Yeah, but
something good happens.
This is the stationary CC. This is different.
Yeah. So you're verifying some other.
Stronger, yeah, this is stronger. So we are very fancies, yeah. Which there are not many examples, actually just one, essentially. I do want just to mention a bit so I don't have a lot of time, but I will try to state where is the action is coming. So let's look at the first step, okay? We collapse, and then we need to do some argument to ensure that we have this U plus cross condition. And very, very shortly, I don't have a lot of time, but simple case would be that we have P0, P1, two elements of the collapse. And by countable, we are collapsing everything below kappa to omega 1, which behave very nicely. We have, so, okay, simplest case, alpha is good point. Whatever it means, it's a pi11 reflection of some things. And we have two conditions, P0, P1, which behave similarly below alpha. Okay, now we want to say that we can find, okay, so, and a bit more, for every sigma and tau above alpha in kappa, we want to find Q0 and Q1, which extend P0 and extend P1. Also, we want to preserve that they look the same under the projection. But the most important thing is that we have this separation. We have some witness epsilon below alpha to Q0 sees that epsilon is in L sigma, but Q1 says that epsilon is not below L tau. So this is the new idea, that we are able to find some epsilon saying from below, epsilon is going to be in L sigma, epsilon is not going to be below L tau, so we have some witness from below, and this witness will assure that sigma cannot be below L tau in the future. So we have in order to do the Lever-Shalach idea, we gotta have some idea or some way to say that two things are incompatible, they are anti-chains or something from below. Like with trees, you find some level where they have different projection, but here we have some epsilon where it's inside one, but not in the other.
This is there's some branch that's new, right? In the Lever-Shalach thing, there's some,
Yes,
like,
yes.
when you're cutting it alpha, there's some branch which is new.
Yeah.
And it's the same thing here. There's some generic information.
Yeah, exactly. Yeah. You need to be able to read generically that there is some difference. And just the end sentence is that this is coming unboundedly often below alpha. This is small levels. This uses the fact that the list has small levels, and this coming from the fact that first alternative fails, and I forgot just to say this is co-boundedly happen. So the fact that you can co-boundedly have this follows from the first alternative fails, and the fact that you can have unboundedly often some epsilon happen, this is happening from the small levels. And the fact that one is unboundedly often, and the fact that the other is co-boundedly often, gives you what you want. Okay, thank you very much.